All right, welcome to the Explainer. Today, we are pulling back the curtain on our digital world to look at one of the most elegant, powerful ideas in all of computer science. Seriously. It's this invisible structure that organizes pretty much everything you touch, from the files on your computer to the internet itself. I mean, just think about it for a second. You have thousands of files, you type something into the search bar, and bam, in less than a second, the exact file you need just pops up. It really does feel like magic. But it's not. It's just a really, really clever system working behind the scenes. So how on earth does it do that? The answer is the tree. No, not the kind that grows outside, but a data structure. This one concept is the secret ingredient to organizing and sifting through just massive, unbelievable amounts of information. Okay, so let's dig in and figure this out. To really get why trees are such a game changer, we have to start with the absolute basics. What exactly is a tree in this whole computer science world? Well, at its core, a tree is just a way to represent a hierarchy. You've seen these everywhere. Think of a family tree, right? Or even a company's org chart. You've got one person at the top, the CEO, the great-grandparent, whatever, and everything just branches out from there. The most important rule? No loops, no cycles. You can't be your own grandpa in a data structure tree. So, to talk about trees, we just need a little bit of lingo. The root, that's our starting point, the very top of the whole thing. From there, you've got parent-child relationships, just like a real family tree. Any node at the very end of a branch, one with no kids of its own, we call that a leaf. And the height? That's just a simple way of saying how many levels deep the tree goes. Got it? Good. Now we can see how they actually work. Okay, so a tree is a hierarchy. Cool. But how does that help us find things so incredibly fast? Well, it turns out by adding one simple, brilliant rule, we can give this structure a genuine superpower. This right here, this is the secret sauce. It's called a binary search tree, or a BST for short, and it has one very strict rule. For any node you're looking at, everything to its left is smaller and everything to its right is larger. That simple property creates an insane amount of order. It's not just a random hierarchy anymore, it's an ordered hierarchy. And that changes everything. And this is where the magic really kicks in. Let's watch how this rule makes searching so fast. Say we want to find the number 25. We start at the top, at the root, which is 50. Is 25 less than or greater than 50? It's less. So we know, it has to be on the left side. We just eliminated half the entire tree in one step. Now we're at 20. 25 is greater, so we go right. Then we land at 30. 25 is less, so we go left. And boom, there it is, found it, in just 3 steps. That seems perfect, right? I mean, lightning-fast searches. What could possibly go wrong? Well, there's a catch. A fatal flaw, actually. One that can completely destroy a tree's amazing performance and turn into something kinda useless. So let's think about this for a second. We have to follow our rule. If a number is bigger, it goes to the right. So what happens if we add numbers that are already in order? 20 is bigger than 10, so it goes to the right. 30 is bigger than 20, so it goes to the right of that. 40 goes to the right of 30. You see where this is going, right? And yeah, this slide just lays out the disaster for us. On the left, you've got a healthy, balanced tree. It's bushy, it's short, and searching is incredibly fast. We call this logarithmic time, which basically means you can make the tree 1,000,000 times bigger, and it only takes a few extra steps to find something. But on the right, you get this pathetic, lopsided chain. We call it a degenerate tree. Our search superpower is totally gone. It's now no faster than just checking every single item in a list one by one. So how do we fix this? How do we stop our beautiful, efficient tree from turning into this Tower of Doom? Well, this is where computer scientists got really, really clever. They came up with something called self-balancing trees. You can think of them as smart trees. They actually pay attention to their own shape, and whenever they start to get too tall and skinny after you add or remove something, they perform these clever little shuffling operations called rotations to snap themselves back into a healthy, bushy, and, most importantly, balanced state. And what's really cool is there isn't just one way to do this. There are different strategies for different situations. The AVL tree, for instance, is kind of like a perfectionist. It keeps itself almost perfectly balanced all the time, which makes it amazing for things that involve a lot of searching. The red-black tree, on the other hand, is a little more chill. It allows for a little bit of imbalance, which actually makes it faster when you're constantly adding and deleting stuff. It's a classic engineering trade-off. So far, we've been focused on trees for searching ordered data, like numbers, but that's just scratching the surface. The whole tree concept is so flexible that people have designed all sorts of specialized versions for all kinds of different tasks. For example, take the trie, sometimes called a prefix tree. Instead of ordering numbers, it organizes words based on their letters. Each path from the root down spells out a word. And words that start the same way, like team, T, and 10, all share the same initial path in the tree. This structure makes it insanely efficient for anything that has to do with text. And trust me, you use these things all day, every day, probably without even realizing it. That autocomplete in your Google search bar, that's a try. The spell checker in your word processor, also a try. Even the way the internet routes massive amounts of traffic around the globe is often managed with tries. And then there's the heap. A heap is a tree with one super simple rule. Every parent is more important, bigger or smaller, than all of its children. What does that do? It means the most important thing, the highest priority item, is always sitting right there at the root, ready to go at a moment's notice. It's like the ultimate VIP line for your data. And heaps are the absolute workhorses of modern algorithms. Your computer's operating system uses them to figure out which task it should run next. Pathfinding algorithms, like the kind that gets an enemy to you in a video game or finds the shortest route on Google Maps, they rely on heaps to keep track of which path to check next. So, when you start to put all these pieces together, you realize something pretty amazing. These aren't just abstract ideas for computer science class. Trees are the invisible scaffolding that holds up our entire digital world. Remember that question we started with? How your computer finds one file out of thousands? Well, there's your answer. Your whole file system, with its folders inside of other folders, it's just one giant tree structure. Your main drive is the root, and every single file is a leaf. And it gets bigger. Every single web page you visit, every single one, is also a tree. It's called the Document Object Model, or DOM. Your web browser reads this tree to figure out how to arrange and display everything you see on the screen. The list just keeps going. The compilers that turn programming code into actual applications use trees. The massive databases that power our entire economy use a special, wide, flat kind of tree called a B-tree. Even some forms of machine learning use decision trees to make predictions. They're literally everywhere. So yeah, from searching a single file to browsing the entire web, the humble tree is always there, quietly imposing order on chaos, making things that should be impossibly slow happen in an instant. It really is the fundamental organizing principle of digital information. Which kind of makes you think, doesn't it? What's the organizing principle in your world?